Hey, welcome back. So up until now, all of our animations in JavaScript that we've done it on a 2D canvas. But I've always had this fascination of 3D animations and drawing in 3D and things of that sort. There are a lot of tools and APIs available that will allow you to draw or animate in 3D. One tool that I can think of immediately is Blender, and I know you can have 3D objects and 3D scene renderings and all of those things done in Blender. But today I wanted to take the time to understand how 3D works, right? In particular, I wanted to see or understand how a three-dimensional object is rendered in 2 dimensions. Welcome to CodeSpace. It's just me today, RK. Ravi's out on his personal business. He will be back next week. So let's get started. So today we'll do 3D to 2D projection. And what do I mean by that, 3D to 2D projection? Technically speaking, your computer monitor can only render something in 2 dimensions, right? I mean, because by its very nature, it's a 2-dimensional object, right? So any 3-dimensional thing that it needs to display needs to be sort of calculated in 3 dimensions, but then projected onto a 2-dimensional surface. All right, that's technically what needs to happen. Now, I remember when I first started working with Java used to come with these very beautiful applets, these demonstration applets that you could execute, and just to show you the power of what Java could do. One of the things, or one of the demos that was included along with that, was a molecule viewer. All right. So it's no longer available with modern versions of Java, or recent versions of Java have sort of deprecated that entire. I mean, they've deprecated applets as well. So along with that, I think the whole demos that were showing molecules and all of those things have also sort of disappeared with modern installations of Java. But I found an old demo, so you can still go to oracle.com and download archived versions of Java. And to my utter surprise, I did find the demos. So I'm just going to show you what I mean by that. All right, so you're going to have to bear with me for just a minute, because this is going to, I'm going to have to finagle around the screen. All right, so this is what I had in mind. First things first, let me zoom on the screen. And this allows me to sort of just zoom in on one particular part of the screen. So concentrate your efforts on the right hand side of the screen and you'll see what I mean. This was the molecule viewer that was that was packaged along with Java when you installed a version of Java. So all versions of Java used to come with this demo. So this is, I don't know what exact molecule this is, but this is something that you could sort of spin around and see how this is, you can spin around the molecule and see. I'm not entirely sure what molecule this is, but you could actually just go around and play with this. I'm going to link a description. In the description, I'm going to link the archived version of this applet so that you can also play around with this. All right, so that is one thing that you could do. One molecule that I did understand was this one. This is Buckminster fullerene, if I recollect, and it had 60 carbon atoms arranged in a spherical fashion. So this is Buckminster fullerene, if I recall correctly. All right. So that being said, look at how this is being rendered on the screen, right? So the nearmost objects or the nearmost atoms of the molecule are the brightest, whereas the ones that are the farthest appear hazed out, or they appear distant. So this is in effect, or the Java applet is designed in such a way that it sort of creates an illusion of being in 3 dimension while calculating and showing everything on a 2-dimensional screen. That's what I want to achieve today. All right, so let's get on with it. All right, so this is what I had. I have a canvas, as per usual. And so I have an index.html page. I have a canvas. I'm not sure if I have to do this each and every episode, but you know what? We'll do it because I don't know when you're going to watch this. This may be like the first episode you ever watch. So we'll just go through this exercise. I have an index.html page on which I have a canvas of size 800 by 800. I've taken the effort to ensure that this canvas appear in the middle of the screen. Please don't pay attention to the dev, to this div or to the canvas or to the style sheets. They are not, they're not the best. All right, so I have a JavaScript file wherein I have an init function. The init function initializes the canvas. It initializes the context. The context is where we are going to be performing all of our drawing operations. I retrieve the width and the height of the canvas, and then I call a function called projection. This is where we are going to be doing our 3D to 2D projection. All right, and on this projection, all I'm doing is drawing or erasing the canvas black, right? I mean, I'm sort of drawing a black rectangle, and this will have the effect of erasing this canvas each frame. And then I'm calling the request animation frame, which essentially performs, acts like a looping function. All right. So this request animation frame will call the projection function once again as soon as this animation frame is available, as soon as all of this processing in this projection function is done. All right. So that's about it. So right now, this is what the canvas will look like. What I also have is another JavaScript file, and I have a way to sort of display I have a 3D point. All right, and this is going to be this is essentially think of this as a 2D point, but it has 3 dimensions, a 3D point. In other words, this is also called as a vertex or a node. It's also called either a node or a vertex. All right, and it has 3 dimensions, x, y, and z. We are going to be drawing everything in 3 dimensions. It can have a specific radius. I have set it to a constant called max radius, which I have declared to be 20. All right, so that's like the maximum radius a sphere can have, or this 3D point can have. Each point has a random color, so they can have random colors. I also have a function called as update and draw. The draw function is supposed to, this 3D point is responsible for drawing itself on the context. So a context would be passed to this draw function, whereupon it would just draw itself. And then I have an update function, which I'll use for, a lot of calculations and all of those things. All right. So let's just go ahead and get started and sort of just draw 3D points. Let's have 100 3D points drawn on the screen. All right. How many did I say? 100. So I'm just going to say num points is equal to 100. I'm also going to have an array to hold all of these 3D points. I'm just going to call them points is equal to new array of num points. So now I have an array of 100 points. I need to initialize these 100 points, right? What do I initialize them with? So I can just say for variable, for let I is equal to 0, I less than num points, I plus plus. All right. I can say point of I is equal to new 3D point, Yeah, that's it. Does the constructor expect anything? Nothing. It's just initialized to X, Y, and then 0. So now I have a new 3D point. That's about it. All I have to do now is sort of render them on the screen, right? So let's just render them on the screen. So this is the projection function. And all I have to say is point of I dot draw of a context. We'll also call the update function before we perform the draw. So each point is sort of updated and then it is drawn on. All right. So that's what we have as far as setup is concerned. If I was to do anything over here, refresh the screen, I'm not supposed to get any errors, but apparently we do. So it's called points. It's called points. It's points. Just a little bit of variable correction over there. 3D point is not defined. It's not defined because I've probably forgotten to include it in the source index.html file. 3D point.js. All right. So this a little bit of errors here and there, but I guess we are okay now. Let's see. All right, so there you go. So of course you will not see anything on the screen because we've not given these X, Y, and Z any values. All right, so what we'll do for now is we'll just give them sort of random values on the screen itself. Okay. So in the case of a 3D point, we need to worry about three variables, X, Y, and Z. We know what X and Y are. They are basically need to be contained within the width and the height of the screen. But the Z needs to be contained in what? Basically, what the Z means is that that our canvas can have a certain depth. All right. So Z essentially means that a canvas can have 0 depth, which means it is right there on the surface of the screen, or it has like, you know, it has, let's say, 600 depth, which means it is at the very farthest. So for that reason, we are going to be having to declare a variable or a constant over here, and I'm going to be calling it depth. All right. And for this depth, I'm going to say arbitrarily, I'm just going to assign it a value of 600. So this means that our perspective or the depth of the screen is about 600 pixels. Remember that our X and Y is about 800 by 800. And now if you can imagine this in the third dimension, this is essentially 600 pixels deep. So now we've come to a point where we have to sort of draw this point on the screen. We have 3 dimensions of variables that need to be converted into 2 dimensions. To do this, we are going to be using a formula. All right. So this is essentially where we calculate the scale of the projection. All right. So to do that, I need a variable called scale projected. All right. So I'm going to be creating a variable called scale projected. And for now, I'm just going to assign it to 0. All right. And this needs to be calculated. This scale projected is the one that is going to convert our 3 dimensions into 2 dimensions of projection. All right. So let's see how that works. Scale projected is essentially nothing but the depth divided by the depth by this dot Z. All right. So this is how the scale projected is calculated. Now to calculate the actual X and Y locations on the canvas, you need to do this. This dot, so we are going to be needing a couple of more variables, and I'm going to call them X projected, which is once again supposed to be 0, and the same goes for Y projected. So remember, we have X, Y, and Z. These are the variables in 3 dimensions, and these are going to be projected onto these 2-dimensional X and Y coordinates. And to do that, it's essentially this dot X X projected is equal to this dot X multiplied by this dot scale projected. This dot scale projected plus, all right. So for now, we'll just leave it like this and see if this works. Okay. So we calculate the scale projected, and then we calculate the X dimension and the Y dimension. And now all we have to do is sort of draw this, right? And how do I draw this? I can just say, first things first, I have a color. So I'm going to set a color to this context. I'm going to say context dot fill style is equal to this dot color. All right. So context dot begin path, context dot arc, and arc is supposed to have an X and Y. So that would become my X projected, this dot Y projected. It has a radius, remember. So what is supposed to be the radius? So for now, I'll just say this dot radius. All right. So I'll have this dot radius start from 0. End angle is math dot pi into 2. So that's constants dot 2 pi. So now I have the 2 pi. And clockwise or anti-clockwise doesn't matter. So I have this, and then I can say context dot fill. All right. So this will draw an arc of a very specific color. All right. So now I have the update and I have the draw. Should this work? We will find out. First things first, let's find out if we are calling the update. So I am calling the update, and then I'm calling the draw. And remember, when I'm constructing this, I'm like sort of giving them random values. So if I refresh the screen, I should have random values. Of course, I don't have. I'm pretty sure I've made a mistake. And yeah, so I can spot it over here. Instead of a plus, I had given a divided over here. So yeah, so that's depth plus this dot z, and then you have this calculation, and then you have this drawing happening over here. So if I now refresh, I should see all of the points that are displayed on the screen. All right. Now, what can we do with this? Let's try and sort of reduce the z variable in this. All right. So what I'll do is, after I perform an update, or even before I perform an update, I'm going to say points of I dot z minus minus, so that it sort of goes inside of the screen or outside of the screen. Yeah, let's see. Let's find out. So I'm like doing this, and you can see that they sort of move from a central point on the screen to somewhere off the screen. So what I'm doing by saying minus minus is like, I'm bringing him outside of your projected screen. But there is one small issue over here, and the issue is that they all sort of seem to start from the center of the screen. All right, and to solve that, what you need to do essentially is have have centers of the screen defined. All right, so the thing is, when you talk about depth, the depth needs to start from the center of the screen, or sort of it needs to be at the center of the screen. So that's exactly what we are going to do. And I'm going to have two variables over here, and I'm going to call them x center and y center, which are going to be basically just half of the width. So x center is equal to width by 2, and y center is equal to height by 2. All right. And these two variables, I'm just going to be adding to the projection itself. So I can just say x center, and this is y center. All right. And now if I do that, you will see that they sort of start from the middle of the screen, which is great. The only thing that we need to fix over here is that we started from let's say the 100 to minus this thing. We no longer have to do this. We can like sort of just give them random values from the center. All right, so let's just do that. So that can be a random value between x center and x, from negative x center to x center, and negative y center, and height can be negative y center to y center. Let's see. So there you go. So now you can see that they are sort of popping out of the screen. All right. But that illusion is still basically not complete, in the sense that they are all the same radius. They are all the same radii. And even though it looks like they are sort of coming out of the screen, out of the screen, that illusion is not complete. So let's complete that illusion. How do we do that? First things first, let's fix the radius. Once we perform an update, we will have to sort of also fix the radius. We'll have to ensure that the more in depth it is, the smaller the radius, and the more outside it is, the bigger the radius. All right. So let's just do that. The maximum radius that a ball can have is 20, which I think is a little bit big. So I'm just going to make this 15, because it looked awkward, right? I mean, with 15 radius and everything. I'm sorry, with 20 radius and everything. I'm just going to make it 15 for now. And I can say this dot radius is equal to map it. All right. Remember the map function. So map this dot z variable. All right. So the farther something is, the smaller it should be. Map it between a value of 0 and depth of the screen to 0 comma max radius. So there you go. So now our radius is tied to how deep it is inside of the screen. Let's see how that works, and you will see immediately that oh yeah, so there you go. So what happens is, once the z value of a variable goes beyond 600, all right, I mean, if it sort of approaches the screen, or if it is at 0 depth, it keeps on decrementing, right? It keeps on decrementing. We don't want that. We want to make sure that once z reaches its maximum z, or if it goes beyond 0, it just remains 0, or we don't draw it at all. So we can do something like this: if points of z is less than only if it is greater than 0, then draw anything at all. All right. Yeah. So we can do something like this and we shouldn't have that error. So you can now see that as they sort of come outside of the screen, they become smaller or they become bigger. This is an error. Yeah, this should not be the case. And I think it's because we've sort of reversed the mapping. We just have to sort of reverse the mapping over here. So if it is 0, it means it is at maximum radius. It means it is closest to the screen. If it is at depth, it means that the radius is 0. Let's just make sure that, yeah, let it be like this. Let's see what happens now. All right, so that is now fixed. All right, so as they sort of, the reason why they're disappearing is because they have sort of, come out of the screen. In effect, they have like sort of come out of the screen. So let's watch that again. So I'm not sure if you can see it, but you feel it, but it's actually pretty slow. So I'm just going to make sure that I say minus equal to 5 so that they're at least a little bit bigger or faster. So there you go. So look at what happens over here. Once again, if I refresh, they sort of come out of the screen, and as they come out of the screen, they become bigger, right? All right. What's the next thing that we can do? Remember, things that are farther away appear a little bit phased out, appear a little bit hazy. So let's do that. How do we do that? Very fortunately, Canvas gives us something called as the global alpha. So we can set the global alpha to do that. All right, so how do we do that? I can say, so just like how I have the radius, I am going to say, I'm going to give it a value called alpha, and I'm going to give it an initial value of 1. Remember, alpha is a value between 0 and 1. So yeah, so I have that, and I can say this dot alpha is once again, just map z to it, z to a value of 0 to depth to a value between 1 and 0. That's it. All right, and now that I have this alpha, I can also say context dot global alpha is equal to this dot alpha. Let's see if this works. All right, wow, can you see that? So the farther something out is, the more dimmer it will appear. The nearer something is, the more brighter it will appear. All right, one thing I don't like is that they are sort of disappearing off the screen, so I'm going to fix that in just a minute. And instead of saying if it is greater than 0, then do an update, I can say else, just draw and don't do anything. Let's see if this works. Yeah, so there you go. So once they come out of the screen, they sort of just remain over there. But if you can see, let's also do one more thing. Let's make sure that they always start from, or let's give like 100 to 150 so that they start from, as center of the screen as possible. Oh no, it has to be a value between, no, the more deeper it is, the more, so I can say, depth minus 100 to depth minus 50. All right, so that they can start very deep inside the screen. So there you go. All right. So that's in its most simplest term, 3D to 2D projection. All right. So the more outside they come, the more bigger these points get. All right. And the more farther away they are, the more dimmer they appear. Yeah, I can actually make them last a little bit more longer. All I have to do is say minus. All right, let's do this again. So you can see that they do appear dimmer. You can concentrate on maybe one color on the screen, and you can see that it will get brighter as it gets, nearer to the screen. So they're all near to the screen. And so yeah, so there you go. So that's how that essentially works. Okay, so now what I want to do is, now that we've completed at least the basics of 3D to 2D projection, I just want to sort of create a globe and have that globe spin around, just like we saw that Buckminster Fullerene molecule in the molecule viewer. I want to do something of that sort over here. All right, and to do that, we're just going to sort of remove away things that we do not need. Now, whenever we are talking about a globe, or anything spherical for that matter, there is no way you're going to be escaping trigonometry. So we are going to be using trigonometry as well over here. All right. So first things first, I'm not going to be needing all of this, this z plus plus and z minus minus and all of those things. Should I have commented it out? Yeah, you know what? I'll just comment it out so that when I upload this to GitHub, the code still remains as is. So I'm just going to comment this entire thing and just going to sort of just have the draw and the update. That's about it. All right, so I have the update and the draw. In the 3D point itself, now because we are going to be dealing with trigonometry, or we are going to be basically needing needing to draw a globe, sort of. All right, and to do that, we are going to be needing two trigonometric values. I'm going to be creating a variable called this dot theta, which will be a random value, between 0 and 2 pi. So I can say random between 0 comma constants dot 2 pi. So that's my theta value. I'm also going to be needing a value called this dot phi. All right. So this is phi, and this will also be a random between 0 and pi actually. All right, so this is a random value between 0 and pi. Now what do I do with these? I don't need them to be, so I don't need to initialize the x, y and z variables to these random values anymore. So I'm just going to comment them out, just initialize them to 0 so that we know that these variables exist. Okay. All right, so now that we have done that, we are going to be manipulating these, or we are going to be deriving the position of this 3D point on a globe based on these two trigonometric angles. All right, so these are essentially angles in radians. So we're going to be using them to essentially evaluate our x, y, and z points, and we'll do that in the update function. So what we'll do is we'll say this dot x, to evaluate the x point on the globe, the formula would be this dot. So when I talk about a globe or a circle needs to have a sphere, a circle needs to have a radius, or a sphere also needs to have a radius, or a globe size. All right. So what I'm going to do is create a constant over here called const globe radius. All right, and I'm going to assign it a value called 300, an arbitrary value of 300. It can be as big as you want, or as small as you want. So I'll say this dot x is equal to globe radius into math dot sine of this dot the phi into math dot cos of this dot theta. All right, so that's my x, which is evaluated out of phi and theta. My y would only be the globe radius into math dot cos into this dot phi. That's it. All right, I do not need this. But my z would be, the z would be globe radius into math dot sine into phi into math dot, I think this is also sine into this dot theta, plus I also need to say globe radius. All right, so that's how you essentially create a globe out of a 3D point. So this would essentially be rendered on a globe. All right, let's see if my theory was correct, or if I had done this correctly. Okay, math dot cost is not a function, of course it's not a function. So with that gone, just wanted to make sure that there are no more errors. All right, let's see. All right, so there you go. So that's my globe, which consists of how many points did we declare? 100 points. So we have 100 points sort of put on a globe over here. All right, you will immediately spot an issue over here. I'm not sure if you can see it. I'm just going to zoom in on this. All right. So you see this point over here, or let's take another point. Let me refresh and see if I can get a different result. So what I'm trying to show you over here is that points that are farther away should essentially appear behind points that are nearer to you. All right. Look at this, for example. Those points in pink are supposed to be behind the point that is being displayed over here. But that's actually not what's happening. All right. So if I was to have, if I just refresh the screen, you will immediately see that there is a problem over here. And the problem is that some of the points that are supposed to be farther away are drawn on top of this, because of the nature by which we are creating these 3D points. Remember, we're just sort of creating them completely randomly, right? So you don't know where in the depth. So they might be created out further, but it doesn't mean that the list is in the order of their scale. All right, and if we were sort of required to rotate this globe, it means that we'll have to sort of rearrange them over and over again. And that's what we are going to be doing. So what we'll do is we'll sort these points. So I can say points dot sort, and this will expect a function, and this will be point 1 and point 2, and this would be a function, right? So that would be return point 1 dot scale projected minus point 2 dot scale projected. All right. So over here, I'll first sort these points on their scale projected. It essentially means that you have a random list of points that are of random sizes, but ensure that the biggest spheres are the ones that are in front, whereas the farthest spheres are put at the very last of the list. So if I was to now refresh, you should see that that doesn't happen anymore. So over here, for example, this sphere appears before this one, as it should, and this should also appear on top of this, as it should. So let's see this in action. So we have the update function, all right, where we are not doing any sort of animation or anything. But if I was to do something like this dot theta plus equal to 0.01, sort of increase the angle just a little bit, I should see this globe spinning. I'm going to reset the size of this canvas and let's see what happens. Yeah, so there you go. So that is essentially the globe spinning. Yes, I wish you could see what I am seeing over here. But what happens is that when a sphere goes on top of another sphere, you will see that effect happening. I don't think there are enough spheres or enough points, so I'm going to increase the number of points to, let's say, 350 and see how this goes. Yeah, so there you go. So that looks like a more filler sphere. They seem to be concentrated on the top and to the bottom over here, but then you get the idea of a spinning globe. All right. Yeah. Maybe we can, oh, you know what? They're actually going so farther into the screen that their global alpha gets turned down to almost nothing. And that is not one of the best things to do. So what I'm going to do is I'm going to say the globe radius is only 250. All right. So that they don't go all the way into the screen. So there you go. So there, so I have now sort of reduced the size of the global alpha. I mean, sorry, not reduce the size of the globe so that they don't get disappeared into the sphere, so in such a way that you can't even see the farthest. I'm going to say points on the screen. Okay. What else? Let's see. If I was to make the depth, let's say 800, I want to see what this looks like. Yeah, there you go. That's an even more agreeable globe if you, I think. I think one immediate thing improvement that I can think of is not to play around with this alpha, because there is a lot of what do you say? I mean, when you say alpha, it makes it transparent. So there is a lot of this transparency thing going on over here. So that's something that we can improve on, right? So let's just improve that. Instead of using the global alpha, I'm going to be dimming the color instead of adjusting the global alpha. So how do we do that? If I need to dim the color, I need to ensure that these are all of the same color, because if I just dim them without having to adjusting the alpha, there is a lot of calculation that I need to do. So I'll just leave it at this for now, and I'll leave it up to you viewers to sort of take care of that or play around with that. All right. So that was a 3D to 2D projection. 3D to 2D projection that I wanted to sort of play around, understand how 3D to 2D projection works. I hope you have learned something today useful. I'll upload all of this code to GitHub, and you can also play around with this animation. We've received some more ideas for the next episode or for our upcoming episode. But the next episode, what we'll do is we'll do something with Pi. Okay, why? Because next Sunday is, I think, March 14th, which is internationally known as the Pi Day. So we'll play around with Pi calculation next week. All right, but after that we do have some episodes lined up. One episode idea that we got from one of our viewers, Animesh, was compression, and in particular he wanted to know how video compression works. Now we sort of have an idea of how to do video compression, or at least how traditional video compression works, but we sort of want to put that in practice and see if we can achieve video compression on our own. Now this of course will take a little bit time for us to achieve, so just give us some time before we can actually sit down and work on that. All right, that's all I had for this week. Do join us again next week. Thank you so much for joining. Do tell your friends, subscribe to our channel, like, share and comment our videos. Thank you so much.